Welcome to class. This is Internet Part 3, and we're going to get started here looking at Internet protocols and packets. This is the Lit Media Workshop. I'm Dr. Linder, and this is basically like a flipped class where we learn about things, so I hope you enjoy this. We're going to go over some things like protocols. What is a protocol? Where do they come from? We're going to go over, in particular, HTTP. We're also going to go over packets, datagrams, IP versus TCP addresses. So, all of this has to do basically with sending messages over the internet, which is the basis for how we actually get the content that we see, whether we're playing video games or streaming videos. This is the nuts and bolts of how these things work. First, we're going to talk about protocols. A protocol is something that defines kind of a script for acting in real life. In computers, it's almost like a kind of etiquette. When do you do things? What things are you allowed to do? What is something that that is allowed and expected? What are the limits? These are all things that will be described as protocols, and these are sometimes defined by governing bodies. For example, you might have something like the WC3 or the IEEE. All of these organizations, they help people work together, even companies that might be in competition, by providing standards where they can be interoperable. That means they can operate together even though one designed it over here and another designed it over there. So it's very, very important things here. It's important for both people and systems to know what to expect from each other. You might have heard this referred to as a social contract. With computers, it's extremely clear what the contract is. Some examples of protocols would be TCP, FTP, HTTP, SNMP, and DNS. These are all just they probably just sound like weird buzzwords, but they all mean something. TCP is what the internet is built on, so it's kind of like a sub-protocol. FTP, file transfer protocol. It's for copying folders and files. HTTP, we've already heard about that. Hypertext, SNMP, I'm not even sure how popular that is these days. That's for things like email. Email is still popular, but there's also IMAP, and it's so complicated. DNS, that's for resolving something by going from a domain name like google.com to IP addresses like 5.5.5.5 or 8.8.8.8. That's Google's DNS server. We have protocols for everyday life, and during our discussion, we'll actually try to practice some of these, and we'll try to decide if we can come up with a good, a good set of steps for people who might need to navigate the social realities that they live in. For example, you might have a protocol for when you meet someone. You might have had your parents tell you to do things when you weren't following the protocol. There's a protocol for apologizing. I'm sorry because of this. I was wrong. Will you forgive me? That's kind of a very common template for actually engaging in the act of apologizing. There's a protocol for answering the door, where maybe you don't come right away or open the door right away. If you're knocking on the door, you don't bang on the door really hard. And the protocols we use might depend on exactly not just the act of what we're doing, but who's involved. For example, if you get a call from a friend, you might say, "Hey, what's up?" If you get a call at work, you might have to also specify something like the department that you're working in.
Good morning, AGS Nerd Studios.
In computer security circles, oftentimes they use the name Bob and Alice to represent two of the parties that might be exchanging communication. So let's say that this is a protocol for meeting someone. Bob says, "Hello, my name is Bob." Alice says, "Hi, Bob, my name is Alice." Bob says, "Nice to meet you." Alice says, "Nice to meet you." Or maybe she would say likewise. And so this kind of goes on, taking turns. One person talking, the other person talking, exchanging ideas until some point. Another kind of protocol you might have is for buying something at the store. You might have somebody who's selling things at a counter someplace, right? And in this case, this is Alice. And then you might have Bob. Bob is buying something at the store, and Bob is going to need some things, right? He's going to need some stuff on the table. He's going to need some money in his hand. And he says, "Hello, I'd like to buy this." Alice says, "Okay, that'll be $7.12. Bob says, "Hey, here's $10. Alice says, "Your change is this." Bob says, "Thanks." Alice says, "You're welcome." Now, this isn't the only way this kind of conversation could go, but it shows you that when you're actually acting, you're having conversations, regular parts of communication have to do with a protocol, even if that protocol has not been codified by a very specific technical document like the WC3 or the IEEE would provide. Instead, our everyday conversations, they have certain things in them, right? Here's another example. Answering the phone. This is like in a company context, and I'll show a clip that explains this a little bit here. So,
Burton, Whiteside of Universal calling. Could you give me the complete figures on our last year's purchases?
Be glad to, Mr. Whiteside, but that'll take a few minutes. You prefer to wait, or shall I call you back?
Well, I am pretty busy at the moment. Call me back, please.
As soon as I have the figures. Your number is...
Dawson, 81237.
Dawson 81237.
Yes, thank you. Goodbye.
Goodbye.
in that clip, he answered the phone. He talked about what department they were actually in. Then he answered some information. Alice asked, I can't remember the person's name, whatever he was. They're looking for a report. They're looking for additional information that can't quite be given in the right amount of time. And Bob gives some choices. Should I call you back? It will take a while. Or do you want to just hang here on the line while I do it? But it's going to be a while. And Alice, the other party on the phone, says, yes, here's my number. I want you to call me back. And so, you know, this clip is basically from an old guide for people answering phones in businesses. And this is still the kind of vibe you get when you make a call to a business. Now, in both of these cases, there's something that's kind of similar to this IP packet. You have things like header information. This would be things like context, where something is going, who it's going to, and if you were to actually give an actual letter to a post office or to a business where it would go and be routed internally, this is how it would go. You might have something like a name, a number, or an address. From, that's like the source, and then a to, name and number and address. Then you'd have data, and then there would be some kind of a definite end in that packet, in that information that you're sending. And in the case of a telephone, you're hanging it up, you're placing it on the receiver.
Oh, yes. And when you hang up, put the telephone securely on its base.
In the case of an internet communication, it just stops sending the data that was expected to be sent. Okay. Now, the internet has these things called IP packets. This is the most basic, small, fundamental part of what actually happens on the internet. We've already talked about how internets are routed, how they go from one place to another place, just like telephone lines.
Could you tell me something?
Sure, if I can.
Where does this wire go?
The cable then travels from pole to pole until it reaches our central office, where all the little wires are connected to switching equipment.
Now, I'm not going to get into super specific details, but this is basically like all the information in like a small size here. And if you were to actually look at the actual numbers in the individual packets, this is kind of the content. This is a map of the content. You have the version of the IP protocol that it's using. And you have over here, you have a total length. That is how long the actual message that we're looking at right now is. We have a time to live. We have a particular protocol that it's using. It's got something called a checksum, which I may or may not explain. But basically, this basically just makes sure that the message hasn't been altered by adding up a bunch of numbers in the actual message. And here's more of our header information. Here's really the important parts here. We have the source address, the destination address. Then there's some options. These options for HTTP might be something like get or post or whatever. And then we have our data. And this can be up to about 65K. To put that in context, a 65K image would be about this big, and maybe an image about this big on your computer screen would be something like maybe a megabyte if it were a raw image. So you actually have to reassemble all of these IP packets if you're sending something that is a reasonably large kind of a size. Back in the day, maybe you don't have to send 1 or 2 IP packets to get something meaningful. But these days, an actual message is filled of, thousands or tens of thousands of IP packets. So to talk about IP packets, we also have to talk about IP addresses. Up until maybe 5 years ago, pretty much everybody was using IPv4, and that had a limited amount of packets. And the number of packets, the number of unique addresses was about half the population of Earth, about 4.3 billion. Whereas nowadays, more and more places are starting to use IPv6, which is essentially infinity. It's a 10 with 38 zeros behind it, so a very, very long number. The IP4 version, which you're still probably using, at least on your local network, it looks like an address that is made up of 4 numbers. 1, 2, 3, 4 different numbers. These are all 1 byte long. 1 byte is the same as 8 bits. And 8 bits can have a number between 0 and 255, so that's why it is. In this scheme, the source sends the packet, and the destination receives the packet. Remember that in our network, we're using directed arrows. These are lines that have arrows on them indicating where the information is actually flowing. Here's an example of running something called ipconfig on a computer. This lists a bunch of different information. It includes things like your actual physical address. This is basically just a random number that's given to your network card. And that random number given to your network card represents the actual device. So if you restart your computer, it stays the same. Whereas your local IP address, this is something given to you by your DHCP server. Usually this DHCP server is basically your local Wi-Fi box. It also mentions something called DNS. This again goes from something like CNN.com to an IP address like 5.5.5. Let's say 25. And so if you're just on a local computer and you're running something like a LAN party, you bring 8 people together, you connect them all to your router, all of your computers would probably have addresses like this: 192.168.1, maybe 1.1, 1.2, 1.3, etc. And that is, over here, you might have like a .1 and a .25. And this would allow everything from this router to be able to talk together. So this computer could end up talking to this computer. Maybe somebody's hosting a game on this computer, and everybody's computer ends up talking to this computer by sending these packets. This is a very standard way that things still work, but how does your computer go from that router into the rest of the internet? Well, that looks something more like this, where physically what you have connected is something like your actual PC. Your actual PC goes into your router through something called an Ethernet cord. Let's see if I have one laying around real quick here. This is an Ethernet cord. This is like 100 feet long. it has something in the end that looks like this. And that is actually something like a very fat, a wider telephone kind of cable there. So it's having a little trouble totally focusing on it. But these are the kinds of cords that connect from your own computer to your router. So your router, which is sitting here and gets that information sent to it, also is connected to a modem. And this modem is connected to your local internet service provider, which allows you access through a gateway into the rest of the internet. So it allows you to reach out and try to talk to somebody, and once you reach out to them, they can come and talk back to you in terms of your actual computer. So let's take a look. So this wired internet Ethernet cord looks a little bit like this blue cord right here. Right over here. You have Wi-Fi connections that end up in the same place. So if you're connected through a tablet, it goes to the same router. And your modem is usually connected through some kind of a coax cable that looks something like that. Now, once your internet, which is way over here, still kind of small, once your ISP goes out here, then it gives you access to a whole web of computers. Each packet has something called a time to live on it. And every time it makes a hop, let's say it starts at your computer, it might start at 10 here, and then go to 9 here, and then to 8 here, 7, 6, 5, and on and on and on until it gets to its destination. And hopefully it's above 0, because if it's not above 0, then you assume that there's something wrong with the network, and you basically give up and let the packet just die on its own and stop being forwarded. Now here's something called a trace route. And I got this from traceroute-online.com. And you can run a trace route on your own computer, but what this does is it's going from this particular host name and making 13 hops to eventually get to the server at yandex.ru. You might be able to guess that RU stands for Russia. And so this is a pretty significant hop from the States to the Russian nation. And it even visualizes this. It takes about 200 milliseconds when it gets there to the actual hop destination. So it's starting here in this little spot, moving here, eventually going up here, and intermediately in some of these hubs, like this hub, it's making a few different hops, maybe within the same server room or someplace extremely local. So pretty interesting. 200 milliseconds is about the same as 0.2 seconds. So you think 1, 2, 3. If you divide a second by 1,000, then you get 1,000th of a second, a millisecond. So 0.2 seconds is like bop, or bop, 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 baby. It's pretty fast. It's pretty fast. Now, if we did the same thing, but instead of going to Russia, we went to China. This is a website in China, and it goes all the way from over here to some kind of like a YouTube-ish thing on China. It takes about 17 hops, and the time that it took to do that is a little bit longer, but relatively the same. So if you look at the average time it might take to get from one place to another place, this can vary from places like New York to Washington, D.C. I don't know how far this is. It's probably like maybe 100 miles away, 200 miles away at most, versus New York to London, which this goes all the way across the ocean, so it makes sense it would take, more time. This is from New York to Sydney. This is in Australia, so it takes an even longer amount of time. It's got more to go through, more hops, and just more distance as well. And then I'm not sure what this means. RTW on equator, but it's just more distance, more time. So it does make sense. The closer you are to an internet source, for example, if you're having your own LAN party, you should be able to get to the computers in your own house much quicker than all the way across the world. Now, the internet has all these different packets as well, and we talked about this 7-layer OSI model, and protocols are built on protocols. So we actually have this link layer down here, and we have this internet layer, which this is what we were talking about, this IP protocol. And the request comes from an application, goes down to physical actual interfaces like physical routers through physical cables, and then comes back up through an application level. And when we say application layer, we're not actually talking about a web browser. We're talking about the internal thing that the web browser talks to. So what makes UDP and TCP different is UDP is what you would use for something like a game. And in this model, you might send a packet that goes a place and then dies, and then you don't care anymore, because the next packet that you send actually has more up-to-date information. Whereas TCP is more for when you're sending things like files. So FTP is built on TCP. Most of your websites are built on TCP. Maybe some of your streaming is based on UDP, because what matters the most is the most recent information, not the most accurate and complete information. So that is the big difference between those two. And the way that TCP is good for completing files is that once it kind of makes a path around all of the different routers that it goes to, it says, hey, I'm going to stay alive for a while here, so I'd appreciate it if you kept this open. So once it finds a path, it kind of punches a temporary pathway that stays alive for as long as a particular session, where this session might last for 10 seconds or a couple of minutes, rather than saying, I really want this just as fast as possible, and it doesn't matter if I lose some of the information. HTTP is built on TCP. And like an etiquette or a kind of a protocol, it defines a bunch of valid actions. The one that's the most common is called GET. And this GET essentially is just when you're receiving information. You're requesting to receive information like an HTML file, like in your game that you have created. Now, for example, if you've gone to a website before, you might have seen something like a 404. Well, in HTTP, if you send a GET and you get a 404 back, there's a table you can look up with that information, and that basically says not found. So if you type in a website like CNN.com, and then you type in a slash, and then you just put garbage here, you'll probably get a 404. Maybe we'll try that real quick. So I just went to CNN.com, and I typed in CNN.com, and then a bunch of this garbage. And then it looks like we get a 404 for this information. 404 means not found. Okay. So there's other things as well here that are in the standard, like post and put and patch and delete. These are all hints for the server. So once an application starts here, an application like a website, like the Chrome browser I just used, asks for that information. Eventually, it's going to hit a server, and it's going to come up back this other way and eventually give me my information back. Let's look at just one example of this. I don't want to belabor the point, but I think it's nice to see in context everything that's happening here. So this is quite a bit of information here. Let's just take it one at a time here. And the way that this moves is, first it moves down this way from the application layer to the physical layer. Then it travels over the world, or to at least another computer somewhere. and it bubbles up in the opposite direction and goes this way. Once it's rendered, it sends another packet back down, way over here, through back to the client. And it might send several different packets in order to correctly reassemble the information. So, for example, I would request a user web page from CNN.com. This would hit the application layer. Then it encodes that information and formats the data. This changes it basically into things like, things that a computer can understand, and you might have some kind of encryption there. Then we go through the session layer. This session is basically controlled by our TCP, which manages this conversation, and this might include things like cookies as well. Then we go through the transport layer, which chunks the data. So we might have something that's very, very large that gets broken up into different pieces, different actual IP packets, and assigns a port. Your port is basically like a mailbox number in your computer, and that way it's like a callback number for when this server-side part finally gets its act together and makes a call and returns your information. Then at the other part, once you've finally routed this IP package, your router says which MAC address you're using. Now it depends, basically this gets peeled off depending on where a packet actually is on a network, but this outside part of the MAC address allows it to go from an actual IP address to a particular place. Remember, you might have an interface that is connected to multiple different network cards. Finally, you're transmitting these raw bits up the chain through this physical layer. Something receives these raw bits, and this gets relayed over and over and over again until it finally reaches the server, and the server does these other things. So you might spend a lot of your hops through this data link layer, your physical layer, until it finally gets sent up to your server side, and eventually makes it back here. Wow, that's so much work. Wasn't that so much work? It's amazing that computers can do this, and we don't even have to really see all of this complexity. All right. So just to reinforce this, TCP uses this transmission protocol, which means that we have sessions and we can maintain more of a stable connection, whereas UDP uses a user datagram protocol and just tries to get the most immediate information. There's a couple of extra things that we could talk about now. Well, one of these things is encryption. You might have seen on your web browser something that kind of looks like a lock. And that lock shows up when you have an HTTPS rather than just an HTTP. And what that should mean is that between your computer and the computer server, nothing can understand that information. So what is encryption? It's something that scrambles your information, and decryption unscrambles the information. So it's a lot like Morse code, except it's like Morse code that is even more confusing to actually read. And a good encryption scheme, basically you can send it or read it, whether you're the sender or the receiver, but to everyone else it just seems like garbage. Now, I'm not going to get into some of the idiosyncrasies of symmetric versus asymmetric encryption. Basically, it uses math and prime number factorization to make it secure, while also being pretty fast. But just for fun, we are going to look at something called ROT13, which means rotate 13. So if you wanted to get to the N, you would basically start... if you wanted to encode something, you can start here in the clear text ABCDs, or you can rotate it here and get these other pieces of information. This is also sometimes called a substitution script. And in order to encrypt, you move letters forward 13. In order to decrypt, you move letters backwards 13. This represents just a single number shift, but you can imagine encryption schemes. You're like, okay, on Tuesdays we're going to do ROT 12, and on Wednesdays we're going to do ROT 14, and on Thursdays we're going to do ROT 16, and so you have a kind of a refreshing substitution script. This is drastically simplified, but that is what encryption does, and computer systems are extremely efficient at doing this. And even though you have things that can descramble some information, this is very much a standard, and you can basically make as hard a task of encrypting or decrypting as you have time for. Okay, so that brings us to the close for some of this learning part. We're going to talk about discussion and homework, and then after this I have maybe about 15 minutes where it talks about using cards to make a map. So in that example, I'm going to be going over how I made these cards, which are basically hypertext cards. So I've converted this game from one that you did online on HTML to one that you do on cards. So it's important to go ahead and go through that information that I have coming up here if you're a younger student. If you're an older student, if you want, you can skip through most of that information, and instead you will be focusing on more HTML information. So that will apply to the older students and will happen after this part. So here I go over CSS, cascading style sheets, and I add an image to the game. So this is like basically the homework is just to continue on your hypertext game, and then what we're going to be going over in class in terms of discussion is we're going to have an update from the students who have brought their papers and maybe even their thumb drives that have their plans for their hypertext game. And then we're also going to be discussing some of this content, as well as we're going to be designing some everyday protocols in small groups. So if you can think about something that seems like it should have a script that you experience in your everyday life, something kind of similar to the the buying things or trading things or whatever, it might be a good idea to think about that. So what do you do if you want to do hypertext, but you don't actually have a computer that you can use, or maybe you're a little bit younger, you're not comfortable using thumb drives and all of that? Well, you can actually just start with some cards. We're going to do some hypercards. This is for the students that are a little bit younger here, that know how to read and write, but maybe are not quite yet proficient on computers. We're going to start with this from my slides before, and we are going to basically redo the game as a physical arts and craft kind of a thing, and we'll do an imitation of that, and we'll get going. So the first step is you want to get that map written out. So hopefully you've already done that as part of your homework, and coming up this next time you can work on this. Now, before we were talking about a story, and we ended up with all of these different HTML pages that end up starting at start and then finally end with these things. These are our end conditions, and these are our start conditions. So what I'm going to do is I'm going to add the links that used to go here. I'm going to add those in green. So you can go from start, you can go to either breakfast, or you can go to hungry. And from breakfast and hungry, you have to go to school. And from school, you can either go to skip test or to math test. If you end up going to math test, then we're calling that end win. If you go to skip test, then you go to end lose. So before I actually start writing down any of these cards, I have this map. After I have this map, I'm going to take my cards. These are index cards, but you might use something else like a cut up piece of paper or a whole sheet of paper. It doesn't really matter that much. It's kind of up to you. And I'm going to assign a number to all of these pages. So for start, I'm going to put a 1, and I'm just going to add numbers so that I don't get confused about which thing goes where. So I've got 1 to 7 pages. Then I'm going to take each of my cards here and go ahead and give them links. I like this blue color for the front. So I'm going to say number 1 here. Okay, so I have a 7 right here, and I have one of these cards for all of my maps. And we could start in any of these positions that we wanted to, but I think it makes sense to maybe just start with number 1. Another thing you could consider doing is to make this a little bit of a harder game to do. You could scramble up these numbers. You could change their position where they go. This is basically just for instruction. So I'm going to leave them where they are for clarity, and I'll move this kind of to the left as a reference, and I'll work on one of these cards at a time. So next what I'm going to do is I'm going to start with, this is number 1. So I'm just going to put a little number 1 here so I can remember, and I'm going to say, you wake up. And you can stay hungry. I'll just say pick. And then number 2 here would be breakfast. And number 3, so I'll put a number 2 right here. And number 3 would be hungry. Or rather, I'm going to call it skip. Now, my handwriting is not great here, so maybe I will actually redo that card. So, I'm going to have a number 1 here. Then I'm going to write it down like this instead. I'm going to say you wake up. I'll put that at the top. Would you like to eat? And then I'm going to write a 2 right here. Or skip to play a game. And we'll call that number 3 here. So then the player would have those choices. They start at number 1, and these are their choices. They can either go to play number 2 to eat, or they can decide to play a game at number 3. And this is kind of nice because you could expand it to be like a rock, paper, scissors game or something like that. So I'm going to turn this back over. I'm going to toss this other card. And then let's work out number 2 here. So number 2 is eating breakfast. So I'll say you eat breakfast. You have eggs and bacon. Yum. Now it will at the bottom say go to school. And we'll put in these little braces here, we'll put the number for school. which I actually, it looks like I forgot to label this. So I'm going to go ahead and get my gray marker. And I'm going to add an 8 right here. So we actually have a total of 8 cards here. So I'm going to write an 8 right here. And I'm going to turn this card over. Then, so I don't forget, I'm going to go ahead and write a go to school here. So this will be number 8. You ride the bus. And get to school. You want to, what do we want to do? Well, we can either choose to skip the math test or we can take the math test. To play, that would be skipping. But should really take your test. And that would be a 5. Okay. So at this point, we have 3 of our cards made. We have 1, 2, and 8 made. Next, and I'm just going to cross these out. So we have 1, we have 8, and we have 2. So let's work on 3 here. Number 3 is you stay hungry. But I think we decided that it would be like you play a game or something, right? So you play video games in the morning. When you get hungry, your mom says, go to school. And then we'll put in this link, which again goes to number 8. So that's number 3. Now we're going to do 4. So 4 will be, you find a kid to play marbles with. You have so much fun. The time flies. And then we'll just have our little end condition here, which in this case is end lose and will be a 6. So that's 4. Now we'll do 5. 5 is you take the math test. So you remember to take your math test. You feel good. and scored an 89. Then we'll go to this end win condition, which is number 7. I like to draw my 7s with a little slash through it. Okay, so that's number 5. So we've done skip test, we've done math test. Now we have 6 and 7 yet to do. So for number 6 here, this is the lose condition. I'm going to write that at the top. You lose. And on the other one, I'm going to write you win. When you lose, I'm going to say something like, you ride the bus home and some kid asks how your math test went. Okay, you cry. So sad. Then we're going to take you right back to 1 here, to the start. And you can start over again. One more card. You ask a kid how they did on the test when you go home. They cry. And then you could try it again, try it a different path. So there we go. We have all of our cards ready now. I've marked all of them off, done. Here they are. Now what you could do is you could spread these out on a table and then kind of retake it. So I'm going to do something like that. I'm going to start with number 1. We're going to just run through it real quick and just do one of the possible options here. Okay, so number 1. You wake up, would you like to eat or skip and play a game? I'm going to skip and play a game, so I'm going to try to find number 3 here. Here it is. Number 3 says, you play a video game in the morning. When you get out, when you get hungry, your mom says, go to school. So that's on number 8. So I'm going to go to school. Once I get to school here, it says you ride the bus and get to school. You want to play, but should really take your test. Well, today I'm just going to play. So I'm going to find number 4. Here we are. And it says you find a kid to play marbles with. You have so much fun that the time flies. Then I should go to number 6. Here's number 6. And it says you lose. You ride the bus home and some kid asks you how your test went, and you cry. So sad. So what's kind of fun about this is you kind of end up with a story here, right? You can look at every card, and it makes up a story. And if you had a lot more cards, or the cards were more like in circles, you might not be able to do this, but this is a great way that you can prototype a website, or you can actually just do this assignment if you're a little bit younger, like this, instead of having to do any actual coding at all. So I'll try to bring these to class so you can play with them. Okay, so for our HTML game, for the older students, when we're doing this project, we're going to go over just a couple of things here. One is basic CSS files. So to do that, I'm actually just going to create a new file. I'm going to call it a text document for now, but actually I'm just going to call it main.css. Yes, I'm going to change it. Then I'm going to open up my notepad. I'm going to drag in main.css so that it opens up. Yours might look slightly different depending if you're using Windows 11 or Windows 10 or whatever. And I think I'm just going to paste in. So this is my main.css. Now I should be able to do things like change certain things according to what I write down here. So what is a CSS file? It's a cascading style sheet. This means that you can have basically like a hierarchy of styles that come into play when certain elements are rendered. Let's see what that looks like in practice. In order to actually use a cascading style sheet, you have to change some code to include that file. So first, I'm just going to do just a very basic let's just change the color of the header. So instead of H1, which I think I have an H1 in, we're going to start with start. So if I look at start, looks like I have HTML, I have body, I have this. What I actually need to add is something called a header tag. This is where like some of the metadata goes for HTML. Then I'm going to copy this this link relative style sheet. So I'm using a style sheet and I'm calling it main.css right here. So it goes link relative style sheet is this thing, just like that. And I don't think it matters, but I'm just going to put this right here like that. And so instead of having the color of the text be black, let's make it blue or brown. Let's see if that works. Hey, it worked. Now start is actually brown. And I could do some other things too, like I could try to change the size. And so let's take a look at where we would find some of those properties. CSS reference. We can reference these properties at W3 Schools by just kind of Googling CSS reference. And here's a bunch of them, right? We could look for things like text size. We have text, decoration, emphasis, indent, blah, 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 blah. How big your text is sometimes called the font. So this one's called font size. And if I click on that with my middle mouse button, it opens up a new tab. And it tells me about these different ways that I can represent this. So I kind of feel like this start, if I have it at regular 100%, is not really big enough for what I want. So in this H1, I'm also going to say size. We'll try this one. It's not changing because I didn't write the right thing down. I just wrote down size when I should have said font size. If I change that, then large is actually too small. So I'm going to say 500%. I'm going to refresh this page. And there we go. That's about the size that I wanted. Then I'm just going to add the paragraph tag as well right here. And I'm going to make this also have a much bigger font size, which we'll say is 200%. And that looks about right compared to what I want. So in order to make this change happen, I'm going to have to change all of my HTML files to all include this information right here. But the great thing is if I copy this header information to all of these other files, which I'm going to do right now. This goes after HTML and before body. And I'm hitting Control S on the keyboard to save this. I already did start, so I'm not going to do that one. So now, if I refresh this page and I start clicking on these different things, then they should all have this this change here. But it looks like I must have missed breakfast, which is kind of funny. Okay, so now if I refresh this page, there we go. So I can get on the bus, I can take a test, I can go home, I can restart the game. Everything looks good. There's another thing that that you might want to change, which would be the background color. So if you go back to the CS page here, where it talks about all these properties, and I'm going to try to include this in my references for the class here. I believe you can do a background color right here. So you can take this background color and we'll just copy this right here, and then we will paste it into this main.css, and this belongs to the body tag, and that's why it is shaped like this. I'm going to change the spacing because it'll look better. And if I save this right here and I refresh, now we have a coral background. What if you wanted your own custom color? Well, in something called Paint, it will show you something called HTML color, and HTML color is represented by basically red, green, and blue. We might talk about this a little bit more in the photography section, but let's say that I wanted this nice light pink. I'm going to click on this nice light pink. I'm going to go back to this custom colors thing, and right here, the key thing to see here is this hashtag, and if you copy that hashtag, you can actually go back to our other application here, our notepad application, and we will just paste that value and we'll get exactly that color. So we'll go from coral to whatever this is, and if I hit refresh, there we go. It's a nice light pink. Pretty cool. Okay, the only other thing that you might want to change here would be to start actually including some images. And this is where Paint also could come in handy. So I'm going to hop back into Paint here. And let me think about what kind of image I would want. So, the way that you include an image inside of HTML, let's do this just at the start. We're going to put it in its own paragraph at the beginning. And you say img for image, src for source, and in that source, you put in an image file. And if that image file is in the same location relative to where you are already, then you're good to go. So I'm going to create an image in Paint, and I guess because you're just waking up, it's going to be a pretty simple image. I'll make it about sort of like a squarish image, and I know I have a pink background, so I'm going to just use this paint bucket to fill it up. And then I'm going to use some colors, which will be, and we'll do it in what goes with pink. Maybe like a nice, we'll just go with black actually. And so I'll use this brush and I'll just write some Z's here. There we go. Now, if I save this image right here, it's going to ask me where I want to save it, and I'm going to go to this folder, which I already have all of my information in here. I'm going to hit Control X to cut that information right here. You could also go here and hit cut or copy. Then I'm going to hop right back into my my save as dialog here, and if I paste that right here, then I know I'm in the correct folder. And just to keep things consistent, I'm going to call this start.png. Now that I have that PNG file, you could also save it as a JPEG file. I mean, you could even save it as a bitmap file, but you probably shouldn't because it's not compressed. I'm going to add that here as start.png, and I'm going to save this. Once I save it and I hit refresh, there we go. There's my image. Now, you could copy this for all of your pages. You could style these pages how you want. And you could look in this CSS background color property area to figure out how you want to do that. Okay, so see what you can get done. See what you can do. If you can bring it on a flash drive, that's great. We'll talk about it more the next time we meet. Thank you very much.